and welcome to the Haber Process and Dynamic Equilibria. This is definitely going to go over 2 videos because I talk too much. Anyway, hello. So the Haber Process was originally discovered or invented by 2 men actually, Haber and Bosch, for the First World War. Its main reason to be found was to obviously create this substance here, ammonia. Ammonia is a main constituent of explosives in the form of nitrates. Nitrates are actually very explosive, and that was its main purpose and why so much money was being put into it to form that. However, actually one of the best things it's ever done is actually it's managed to feed a third of the population of the world, because it is great as a nitrogenous fertilizer. Nitrates are fertilizers as well. What we find is little plants become big plants with this artificial fertilizer. In the past we had to use manure and guano, guano being bird poo, and actually made some countries quite rich trading in their bird poo, particularly South America and Africa, where they have large colonies of seabirds and penguins. Anyway, the problem is, though, with many things, is when you tamper with a system, actually it can cause problems, and it took a while before we realised that actually if we don't use these fertilisers, artificial fertilisers, correctly, you can get these problems. So here actually we can get some overgrowth in our rivers and lakes, and sadly in the end it can lead to death of the animals that are there. This is a biology thing, but you need to be aware of it in chemistry because it is an effect of the chemicals themselves. So I'll go over it quickly, but you might want to check your biology notes as well. So what it is the fertilizers make the algae in the rivers overgrow. Algae can produce a lot of themselves very, very quickly, and when they do that they cover the surface with their algae beings, if you like, and stop sunlight going further down through the water to the normal plants, if you like, the other plants that are there. Those plants sadly die, and when they die and they get decomposed by the decomposers, there becomes a lack of oxygen as those use those up. And because there's a lack of oxygen, there's no plants making it anymore, the algae is just releasing it straight into the atmosphere. You find that the fish start to die, and so actually you get a lake or a river that is now all intents is dead because of this. This process is called eutrophication. So actually there is, when we're looking at fertilizers and what we're doing today in the Haber process, we need to keep in mind that there are actually other factors that if not used properly can cause problems either to nature or in war. Anyway, let's get back to the Haber process itself. So the Haber process is actually the formation of ammonia, and again very simple. We've got nitrogen from the air. We know that in the air nitrogen is the main part of air, about 78%. The hydrogen comes from natural gas that's formed. We don't need to know how that happens, and then ammonia is formed. We've got a balanced equation here, but this should be something that you haven't really seen before. If you look at it, it's not a normal arrow. It's actually a reversible arrow, a reversible reaction. It means you've got a forwards reaction going that way and a backwards reaction going this way. So what it means is they're happening at the same time. It means that a lot of reactions, like an explosion, it happens, that's it. But in this one, if you imagine, you've got those parts that are forming the reactants that you started off with. I know it sounds a bit crazy, but it does happen. There's quite a lot of things that do this. So, looking back at here, what we're saying is you've got this reaction in that way, you've got that reaction here. So as ammonia is being formed, it's breaking down. Now that's not what you want if you're a manufacturer. They want to force the forwards reaction to the right. They actually want ammonia to be formed. So they have to make that happen. But I want you to think about what they've got to try and do. They've actually got to try and force it to go one way. Naturally, when the reaction is happening, you'd get one of these set up. This is called the dynamic equilibrium. Sounds awful, but actually is quite easy to understand. As long as you think about a thing that you did when you were younger. That's right. I want you to imagine an escalator and you walking up an escalator, but you walking up the down escalator. As the escalator moves down and you try and move up, you actually stay in the same place. There's a lot of movement. There's the movement down, there's the movement up, but overall, no movement. That's what we call dynamic, the moving part, up and down. Equilibrium, equi meaning the same. So actually, loads of movement, no overall change. That's what a dynamic equilibrium is. So when this reaches dynamic equilibrium, lots of movement. So you've got these forming the ammonia and the ammonia forming back those. So actually it looks like there's no overall change. As a manufacturer, that's not what you want. You need to force it in a direction. So actually we need to be able to tamper with it and alter it. Because the higher the yield, the more Wonga you get. That's what manufacturers want, that's what they're interested in. But any change you do will cause the system to alter so equilibrium can be reached again. That gets more complicated, and if you go into A level you do loads on this. So, typical things, remember we talked about what affects reactions before, the 4 things that affect, and we're going to look at 3 of those. So temperature. Temperature can actually help if you alter the temperature. The forward reaction itself, from here, this reaction, nitrogen and hydrogen becoming ammonia, that's the forwards reaction. When I talk about that, that's what I mean. The forwards reaction is actually exothermic, meaning it gives out heat to its surroundings. Whereas the backwards one, the ammonia, has to be the opposite, because energy can't be created. So it's not quite what I mean, but you know, conservation of energy and all that malarkey. Anyway, so the opposite is true. The ammonia, when it breaks down, actually takes in heat from its surroundings. So if we cooled this situation down, if we cooled the scenario down, it will actually force this forward reaction to happen. So that's what we want. We want a cool system, and then we get more ammonia being formed. However, there's a problem, and there's always problems. And whenever you're a manufacturer, when it comes to chemistry, there's compromises all over the place. So this is the first problem we have. A low temperature would mean that the reaction would be very slow, really slow. I mean years slow. I don't know about you, but as a manufacturer I don't think I'd want to put all that money in and get very little out of it. So you have to try and alter some things. We know temperature needs to be low. We can change the pressure of something. So what we're looking for this time is we need to understand something about what is there. So let's have a look at the equation again. You've got 1 ammonia and 3 hydrogens. That means overall you've got 4 gas molecules on this side. Okay. Over here there's only 2 ammonia, or 2 gas molecules. So if we compare them, 4 gas molecules over this side means actually, if you like, there's a lot more pressure and there's a lot more gas on this side than there is over here. There's only 2. So if you think about squashing a balloon, it always goes in the place where there's lower pressure. Wherever it can, it will push out that way. So from squash it, higher pressure is going to force it that way. So actually, if we put this under high pressure, we're going to encourage that forwards reaction. The higher the pressure, the better it is.